Swayam Prabha. Digital India. Educated India.
Welcome to lecture 3 of week 4 of the course on Muffler Acoustics, NPTEL course here. In this lecture, we are going to talk about basically 3 different things. We are gradually entering into the elements that constitute a muffler, and the last lecture, if you recall, we discussed things like insertion loss, transmission loss and level difference. So, the objective of this lecture is basically analyze the transmission loss performance of constituent elements, particularly this simple sudden area discontinuity, also known as simple area discontinuity, what I have written, also known as sudden area discontinuity, and simple expansion chambers. But before we do so, there is another thing to be studied, and that is a lumped element representation of a tube, that is basically this bit. So, let us start off with this thing, and the idea is to basically discuss different implications of the lumped system analysis that is basically valid at low frequencies, and how do we represent that in an through an electroacoustic circuit or electroacoustic analogy, and how this is applicable to your sudden area discontinuities and so on. So, we will build a continuity from there. So, if we recall, for a tube something like this from our last several lectures back, I guess probably week 3, few lectures in week 3, probably the 3rd or 4th. If we had a tube of length say L, and this was x, and this is something like this, cos k naught L plus j y naught into sine of k naught L, and j times xi L by y naught, and here you are all right. So, what this expression means is basically your, let us call this equation 1. You are looking at the tube from this end, you are trying to relate the impedance zeta naught or zeta 0 to the impedance zeta at L, that is xi naught and zeta at 0 and zeta at x equal to L are related through some expression, which is basically this expression is nothing but obtained by some algebraic manipulations of the one dimensional wave propagation equation. So, what happens when you have a very low frequency approximation? So, what do you mean by low frequency? What is the term that decides whether we are in the low frequency or whether lumped system analysis approximation can be made or cannot be made? So, this is the term argument of the sine or trigonometric function. So, k naught L, the Helmholtz number. Let me put this again here, Helmholtz number. So, when k naught L is much less than 1, then obviously we can make a lot of simplifications, and then your lumped system analysis will apply. So, we can have different scenarios, of course, like we discussed, either the frequency is very small or the length L is also quite small. So, in either case we will see how we go about it. So, zeta at x is equal to 0, this can be written as zeta at L plus j y naught into k naught L, and divided by j times this thing, and denominator you will have y naught, and what do you get here? You will also get again k naught L plus 1. So, this is only an approximate relation when you have a very low frequency approximation. So, we saw that the expression of impedance at x equal to 0 zeta at x is equal to 0 is related to zeta at x is equal to L, impedance at x is equal to 0 and x is equal to L, they are related by the following expression. So, let us make some approximations, obviously with understanding y naught is C naught by S, and this will happen when you have k naught L is approximately equal to k naught L, and cos of k naught L is approximately equal to 1, because you have k naught L is much less than 1, or it is basically a very low frequency approximation as we are discussing here. So, this all these simplifications are possible because of this thing, and when we further put this thing here. So, plus j C naught S into omega by C naught into L j times zeta at L, and here you get S and the denominator C naught and omega by C naught into L plus 1. So, basically what happens now is that this will become j omega L by S and j to zeta L. Remember, S into L is the volume of the cavity. So, let us say the cavity is like this with wave propagation like along these directions. So, V is equal to S into L, that is what we are going to get. So, under such a situation you get we can combine S into L as volume of the tube, and here we get omega and C naught square. So, all these terms we should recall, we are seeing all these familiar faces. So, zeta at x is equal to 0 is related then to this thing at zeta at x is equal to L plus. So, that was clearly our inertance. So, if you recall, the inertance for a thing like this, for a structure like this, for a small tube sandwiched between two large cavities. So, the impedance or the inertance was given by j omega L by S, where S is the cross sectional area, L is the length L. Similarly, what is this particular term? It is ZC. So, again recall that ZC is equal to, that is a compliance, your C naught square. So, basically what is happening then, that zeta is equal to 0 is equal to zeta at L plus Zm, and then if we simplify this expression, then j omega ZL, and immediately we recognize that the compliance of the cavity is C naught square by j omega V. So, then this will become 1 by ZC, and here you will get plus 1, you will get plus 1 here. So, I probably should have written this as L and L here, and of course, you have these two terms, this one and this one. So, now the thing is that what do we do with this expression, where do we go now from here. So, basically what is happening here, that we can probably further simplify based on the condition that we know. For example, what is the all we know is that there is just a tube here, but what additional thing that we need to know is that what lies upstream and downstream of the tube. So, if you recall this figure, so this figure tells you that if you have a tube of whose diameter or cross sectional area is much smaller than this one. Okay. So, when you have such a thing, then of course, this will be dominantly, the volume of such a tube is mostly much smaller than the volume of this one and this one, all right. So, the compliance will be much larger. So, your basically what is going to happen then is that for such a situation, Zm will be basically whatever we get, j omega L by S, but Zc will be much greater than Zl. In other words, zeta L is basically something that is much smaller than the compliance of the tube. So, one can safely ignore the underlying term. So, under such a situation, what we actually get is zeta at x is equal to 0 is zeta at x is equal to L plus Z m, where Z m is j is basically j omega L by S. So, what it means is that if we know additionally or beforehand that what lies upstream and downstream of the tube. So, if we have a small tube sandwiched between two much larger cavities, then impedance transfer or the impedance at this point and this point is related to just the addition of the inertance, that is impedance at x is equal to 0, xi at x equal to 0 is the impedance here plus the inertance of the tube at very low frequency. So, basically then this thing is, I probably should have let me make some space here, and so this then is equivalent to your circuit, the following electroacoustic circuit. So, here you have Z m and here you have this thing. So, so this is the electric or the acoustic velocity or the current, and this is zeta at x is equal to 0 and zeta at x is equal to L. So, clearly whatever the impedance we are seeing at these 2 points and whatever we are seeing here, they are related by the relation like I just wrote down. So, the same as next page what I have been writing. So, the thing is that impedance for a tube which is sandwiched between two large cavities, we just need to find out the inertance at very low frequency, and this is the electroacoustic circuit for that. Now, if we have the reverse situation, now let us say the tube is no longer the cross sectional area of the tube is no longer very short or very small, it is basically much larger than the upstream and downstream elements. So, it is something like this. So, recall the situation here and recall this thing here. So, it is much larger. So, and of course, x is measured from here, x is equal to L here, and this is what we are going to get. So, basically what happens in such a case? In such a case you have Z m is much smaller than impedance at zeta at x is equal to L. So, if you recall this expression, when this guy, this particular impedance, that is basically the inertance, that is much smaller than your impedance here. So, then you can ignore this term and just retain this thing. In such a case, what we will get is basically the equivalent impedance is basically zeta at x is equal to 0 is equal to zeta at x is equal to L into Z c by plus Z c. This is what we are going to get. So, that means the element basically has a compliance kind of a behavior, and that acts like a shunt element. So, basically if I draw the electroacoustic circuit for the figure this one, so we will have situation like this. So, this is represented by this thing Z c, and here you have this thing. So, what happens is that the current or the acoustic mass velocity gets split into two parts, one that goes within the compliance and the one that propagates further downstream. So, basically this compliance or the large cavity or the cavity with a large volume much larger than the tubes that are upstream or the downstream part. If you have such a situation, then the element acts like a shunt element and the compliance can be considered as a shunt element. So, then basically when you have such an element, so this element can then be represented, or this expression rather, what it means, it can be represented by the electroacoustic circuit in which the compliant acts like a shunt element ZC. So, the acoustic mass velocity gets split into two parts, one that goes within the compliance and the one that propagates downstream. So, you basically that is how this zeta naught is related to zeta L. So, this expression obviously can be written in the form 1 by zeta at x is equal to 0 is 1 by zeta at x is equal to L plus 1 by Z c. So, that means the impedance or the compliance, this entire thing, and the impedance at this part, just at this section here, they are acting in parallel. So, that is how you get this representation. So, what is the meaning of all this discussion is that it is important to note that what really matters is that how Zm and Zc compare with zeta at x is equal to L. That is the, in other words, the lumped element behavior of a tube is then a function of what lies downstream of it. So, just to summarize this discussion, if the tube in question is much smaller and thin and sandwiched between two tubes of much larger cross section, that is two larger cavities, then it behaves like an inertance. On the other hand, if you have an acoustically small tube, k naught L is much smaller than 1 and sandwiched between two tubes of a much smaller cross section, that is to say the element with a much smaller length, that itself is having a diameter much bigger than the elements on the upstream and downstream, then that element behaves like a compliance with a shunt impedance. So, for typical acoustic filters, that is mufflers, silencers or mufflers, they are also called acoustic filters, low pass filters, because they generally have a low performance or not so good performance at very low frequencies, because they allow most of the acoustic power at low frequencies to pass through, and they generally beyond at a certain higher frequency. So, they are also called low pass filters, and lumped element approximations, they hold at very low frequencies, but just to understand the basic behavior of mufflers, all this will be useful. So, that is the reason that we talked about the lumped element behavior of a tube, because eventually a muffler can be considered in the most simple muffler is the simple expansion chamber. So, in many which ways we can, by studying lumped analysis of such systems, we can get to know the basic behavior of a muffler at very low frequencies. So, basically now we intend to move to the elements that constitute the muffler, and for that let us basically first look at what are the elements that constitute a muffler, and we can go to the slide or the presentation. Well, now we probably need to enter into the simple area or sudden area discontinuities of a muffler and also simple expansion chambers. With this background, I guess it is time that we move to the elements, the very fundamental elements that constitute a muffler. And but before we do so, I guess it is prudent to have a look at the entire structure of a muffler, which is basically your thing like this. Now, this is a schematic or a block diagram of a typical layout of a engine exhaust system. So, what we probably need to worry about is basically this part, the engine exhaust system. So, let me however very basically tell you very briefly about the engine exhaust system. So, you have the intake system here, and there is a orifice noise, there are number of filters upstream of the muffler, and there is kind of a resonator to kill the noise here, and through number of manifolds it comes to the engine sucks in air, and after the combustion takes place, the products of combustion are then let off through your exhaust pipe, and here you have something like a bellows kind of a thing, and there is an airborne noise. Finally, this is your exhaust pipe, this is your tail pipe. So, this is the muffler entire exhaust system that we intend to study. So, we see here muffler 1, muffler 2, you can have, it is not very sacred, you can have very different arrangements, you can have double outlet mufflers also, which is popular. So, basically what I wanted to tell you about is that these are the elements that constitute the muffler. You see a port, an inlet port through which air comes or the acoustic power is incident, and some part is reflected back, some part is transmitted, again some part is reflected back, some part is transmitted, and this process is repeated for the muffler 2. And eventually very less amount of acoustic power is transmitted in the atmosphere. So, that at least for the frequency range of interest, that is how you design a good muffler. And most of the acoustic power then is transmitted upstream, and then there is a lot of power that is radiated out. This is called structural acoustic noise or the breakout noise. So, we are not going to worry about that part, at least in this course. We are just going to focus on things like if you have a muffler like this, if you have a certain element like this, what is, and if you have certain wave incident here. So, what is the ratio of the energy incident and energy transmitted. So, we are trying to study that and log of that. So, basically the transmission loss or the also known as the axial transmission loss, or basically considering the muffler shell to be rigid. Of course, nothing is rigid, muffler shell will vibrate, but we are just trying to study the effects of axial transmission loss or the energy or the acoustic power that is incident on the muffler to the acoustic power that is transmitted downstream. We are just going to study that without regards or without consideration to the noise that breaks out from the transverse surface. So, basically before we begin the analysis of this system and this system, we need to worry about the constituent elements that I have been talking about so far. So, this schematic shows you a sudden area change or a simple area discontinuity, also known as a simple area discontinuity. We will derive carefully how these equations came. Simple area discontinuity. So, figure B or figure C, basically what it tells is that there is an incident wave of amplitude A that is incident at a cross section points marked as 1 and 2, and some part of the wave is reflected back and some part is propagated downstream, which is C. So, naturally there will be some energy that will be transmitted into the atmosphere. So, this is a system where there is a sudden area increment or increase, and on the other hand in this point there is a sudden area decrement or sudden area reduction. So, if you consider a simple expansion chamber like this, what this figure actually does is that it breaks a simple expansion chamber into sudden an area expansion where the expansion is where the area change is positive or the area has increased, and in this thing there is a contraction or the area change suddenly is reduced. So, the idea is to have a impedance mismatch at these ports, so that most of the acoustic power or significant acoustic power is reflected back. So, let us see how it works and how the things are related. So, we will probably worry about that in the coming lecture, and stay tuned for that. Thanks a lot.